In the name of God, the compassionate, the merciful. This is our week 4 of the practice sessions of C++ template metaprogramming. Today is a bit special because we have questions left over from the previous time, and there is going to be some acting involved. Remove this. Why is this thing? Oh, anyway. Now let's see. So before anything else, there was a question from Daniel regarding whether we really need to always do well, let me get to that. So as you can see in this example, there is only one overload for take, which receives a list and it compiles that number, and then it performs a case split in the form of an if statement that sits within the function rather than two overloads, one of which dealing with the empty list, which would be this case, right? Now, Daniel's question was, why do we sometimes have two overloads rather than the case splitting according to the if constexpr that you can see on lines 212 and 213. And so what I responded, in short, is that sometimes that's just a matter of preference. Sometimes you can't do the other way around. And this is an occasion when you can't do the other way. Well, we can do the other way around. Thing is that, so if this goes down to n-1 to 0, we will end up calling the same with an empty pack. And so everything is fine. Whereas if we go to drop, things are a bit different because there are two cases where you want to stop the recursion. One of which is the case when the list is empty, and the other is when n is 0. Right? If you rely on decreasing n or decrementing n until you hit 0, and you don't have this one, then what will happen is that you will have another if statement here, which checks, well, if constexpr, which checks for the emptiness of this pack. Right? So let's see. What else? I think I'm done with this one. Now, there was also one question from James. Well, James's implementation helped me understand why Idris wants to do with that like this. So what they are doing is that they in this code, span is feeding into both the take and the drop lists at the same time, which means that rather than going, let me show the other one first to you. Right. If you do it like this one, which is the PDF from the Estonian University, you produce take, you produce drop, and then you couple them together in a tuple and you return. And each of these is an act of O of n, which means that when you couple them together, you're still doing an act of O of n, but that will involve two iterations over the list, right? Whereas in the implementation of Idris, as well as the implementation of James, slightly bigger. Okay. There is only one go into the vector, right? Now, what this is doing is that it is deciding. So it says that in order to decide about the split at of k plus 1 when the list is non-empty, I will make up my mind about the split at of k with the tail of the original list, and I will save the results in tk and dr for the results of take and drop, right? And right, let's see. And given that this was k plus 1, and we had a head, right? The head should still go to the take part, so that's why you get this one, and the drop remains the same, right? So that's that. And you continue that until you come to the point where you have 0 elements to take, in which case you return an empty list for the take part because it's 0 elements to take, and the remainder as your drop part. All right. Now, thank you, James, for I don't know whether you were trying to copy this or not, but your implementation helped me understand this.
Yeah, I think mine's slightly different, but obviously
right.
This function. So, but yeah, same idea.
Yeah. Mm-hmm. Now, this implementation is roughly twice as fast as our implementation. It's still the same order of complexity. It's the same O notation, right? They're both O of n, but the hidden constant here is twice. Sorry, in our implementation, which is this implementation, is twice as the other one because we iterate over the list twice, whereas this one iterates over the list just once. Okay. Now, announcement. There's going to be an acting soon, and that starts with James coming to the podium. Go on, James.
So I'll share my screen.
Yes, I'll stop sharing.
So share screen. This one. So it's my span function. And the problem is that this line 129 is not, this is not done at compile time. Yeah. It's just a simple auto.
And you want to do it at compile time?
I want to do it at compile time, but I can't do I can't do constant expression auto.
Okay.
For whatever reason.
Now, right. Now, I don't know whether in the future the committee, the C++ committee, will decide that they are going to lift the bar for disallowing ease this limitation. But the thing is that at the moment, what is called the structural binding, which is the part that comes from auto to the right until the equal sign, that is called structural binding.
Right.
is only allowed at well, it is not allowed to become constexpr, right? Now, that does not mean that you cannot force it to happen at compile time. The irony is that you can go to pre-C++11 and make this doable. Now, the way to do that is that you would make your you would replace your const expr with const static const, and then yes, yeah. Now, I think I have never explained to you what static means here, have I?
No.
We discussed, right, okay, we discussed the meaning of static data members of structs, but we never discussed the meaning of static inside functions, including member functions. So here is what that is. It's slightly different. It's slightly different from. You have a question?
No, you said who knows what it is.
Oh, okay. If you want to just explain it, sure, go on.
I think I know, because we use it a lot in the Linux kernel.
Right.
And so, as far as I can tell, if I had a function, say an increment function or a counter function, I could have a static variable inside it, and each function call, it wouldn't be reset. So it seems to say that it's an area, the variable is an area, this is static. It's an area of memory that's sort of shared between all of the different functions. That's in C.
Sorry, but not between different functions, but different invocations of the exactly same function.
Yes, that's what I mean. Different invocations of the same function.
Right.
So it's like persistent across function calls.
That's right. So the thing is that a bit of a compiler construction thing here. Now, the pair of curly braces you see on lines 128 and 134, they are called a local scope, right? Now, the variables that are declared inside that local scope, they will, as soon as the execution flow makes it to the declaration of those variables, and I received the first yawn from Jan. This one was recorded. Don't say that I just opened my my mouth.
I agree.
Okay. So as soon as the execution makes it to the declaration site of a local variable, it gives or it goes to the stack, the compiler stack, which is given to it by the operating system, and it allocates memory for that variable. And when you go, and when you go out of the scope, it just pops things in the reverse order from the stack, right? And so that's called a local, and it's considered bread. What is it called? It's the bread and butter of compiler construction. But there is something else which has a different storage policy, which is the static variables. Static variables they are not allocated on stack, because they have to be persistent across function calls, or across calls to the same function, which means that the next time that the flow of execution gets to the point where the variable was declared, because it is now in another invocation of the same function, the old state of the variable is still in place. Right? Now, so are we good with that? Do we all understand the meaning of static here?
So
Okay.
where in memory is this variable saved?
Sorry, I'm not sure I heard you.
So it's not on the stack, but where else is it placed?
Oh, there is something else called heap.
Oh, it's in the heap. Okay,
Right.
I thought so. Okay.
Is it in the
Yes.
heap?
Well, I think I think they are in the heap. But
Because
you know,
they
not
wouldn't be on Linux. They wouldn't be in the kernel, because that would
uh
require something that could deal with heaps, which there isn't in the
right.
language.
Right. Yes, you're right. You're right. Maybe and maybe I should retract. Well, the thing is that okay. My bad here. They are not on the heap. They are on the static storage of the compiler. Right now, that static
Okay.
storage might be a part of the heap that only the compiler has access to. Right, but that's different from the heap where you do like memory allocation. The programmer does the memory allocation.
Yeah.
Okay. Yep. Now, so now, James, I think you have an error on line 133.
Yes, I do.
Would you like to explain to us what your plus is here?
So my plus is my append function that's defined
Okay.
here. I thought it was nicer to do it as an operator instead of just append. So
Okay.
yeah, it's there.
Okay. Right. Do you know? So can you explain the error message that you get on line 133? I think it was.
Yes. So
Yeah. What do you
invalid.
understand from this?
Well, I do now.
No.
I
What
didn't.
do you understand from it? Yeah. What do you understand?
So the problem, and I'll see if I can map my understanding to the error message, because it's not
Okay.
it's not completely obvious from the error message. Invalid operands to binary expression. So this is the binary expression. And then it says tuple element 0 here, and const std pair list type, aka const list.
Would you like to maybe build so that you have the error message and you can you can highlight the error message for us?
So yes, so we
now,
have
I'd like to take a moment and explain a bit of the error message. Could you please go a bit? Yeah. So you see, a part of this error message is trying to show you the call stack. As you can see, like for example, at the bottom of the this triangle thing that you get at the top of the build messages, right? Now you see that it's at the very top. It says spanner 5 and 6, and then it says spanner 4 and 5 and 6. One and then one line later, it's trying to just show you where it came from to here, right? Now, a part of the art, and I don't know how much of a good word this is, but a part of the art of C++ template metaprogramming is the art of navigating through the error novel, right? So you should be able to, just quickly skim through these lines and say, okay, I understand that at this point you're just telling me that this is my core stack. Now let's get rid of those. Let's get to the gist of the error message. Right. Now,
which is
the error
helpfully
message.
demarcated.
So what does this say?
Well, I have learned that through C++ before, that the easiest thing to understand is when it says AKA. So we have a problem with invalid operands to binary expression. And so it's const list and const list, and they are const because we said it's const.
Yeah.
So TF a const, and it's
Okay.
not happy with the operands. So and the yes, so these two.
Okay.
I think that's yes, that's all it says. So it's saying that it doesn't like the fact that the operands here are const.
Okay. Okay. Now, what did we learn the previous time about this? We have two const operands and an operation which is trying to perform a non-const operation.
Yeah. So the problem is that
right. Now, in the previous session, this wasn't in the recording, but I asked you to show me your implementation of that plus operation.
yes, which is here.
Okay. Now, your plus operation is a member function. Right? Now, that is why in the error message, you know, in the top one that is on your screen at the moment, in the build part of your screen, it says something about this. No, not the one, not that one, the one above. Right. It says something about this. The within single quote, it says no, not come down.
Here,
Yes.
I see.
That's right. Yes. Right. So what it's saying is that, well, let me maybe put this.
If I go to the side there,
right,
that's the whole thing.
So what this is saying is that this is not const. And I told you in one of the previous sessions that this is the pointer to the current instance of the class inside the body of the class, inside the member functions of the class. When you want to refer to the current instance, you have this keyword THIS, right? Which gives you a pointer to that instance. Now, what it's saying is that this is not const. Sorry, this is const, right? So if you read toward the right, you will see the AKA. It says this is const list with empty pack, but the method is not marked const.
Yeah.
Now, how do you mark the member function const?
Well, like this.
Yes, you do that, right? Now, that trailing const is a promise to the compiler that the code inside that member function is not going to change the state of the current instance of the class. Right? Now, which means that it will not manipulate the data members of the class or the struct. As I told you, they are the same. It's only about the private versus public. Now, having said that, for the sake of completion, there are also volatile, mutable data members. So if you declare, if a class or a struct declares one or multiple of its data members as mutables, it means that even when the member function is labeled const, mutating the values of those mutable data members would be fine. Right? Now, so James, can you now rebuild maybe?
There we go.
Yeah, that's you done. Okay, excellent. Good.
Yep.
Thank you very much. End of the acting. So
I remember the other question.
Oh, you do? Okay, go on.
It wasn't a question, but it was you wanted to talk about why we're not, because normally in C++ you would say that all the inputs
Right.
are normally const references,
Right.
or for performance reasons, and yet we're just passing everything in.
Pass by value. Yeah. Yeah, you're right. You're right. This wasn't really a question. This was something that occurred to me myself. So let me just share my screen. So before we go into that, I'm gonna ask Daniel to give us a joke.
Daniel, you're muted.
I'm muted. There you go. Let me think of one. Okay. So here in Norway, it's become very popular to have these kebab stores all around. There's probably like 5 of them where I live, just around the neighborhood. And they're pretty good.
Resource? Did you say resource?
Kebab. Like kebab shops.
Kebab kiosks.
Kiosks, yeah.
Yeah. Like you know,
What?
A place that sells kebab.
Kebab. Oh, kebab.
Yeah.
Okay. Okay.
There you go. So I went into one the other day because I was a little hungry. It's very popular for students, and you know, they have the typical kebabs and like really kebab, something we have in Norway, and something called banjo kebab.
Banjo. Okay.
Yeah. So I thought, do you want? I'll take a banjo kebab. That's new. So you know, he makes the kebab for me, and I start eating it. It's very good. You know, just enjoying it. I start wondering why is it called banjo kebab? So I asked the guy behind the desk, and he points at my shirt. So while I'm eating it, I see it, and I was still I'm like, oh no. There you go. And that's it. That was my joke. A little banjo.
Okay. Yes.
Oh,
Yes. That does that does count as a joke. Don't worry.
Very good. Very
Right.
good.
Okay. Well, I'm sorry for your shirt. I mean, having that happen to oneself as a student away from family can be really disastrous. I can, yeah.
That was my favorite
yes,
shirt. Oh wow.
Yeah, and this is the point where we should spare our tributes to mums. So thank you very much, the loving mums of the world.
Indeed. Indeed.
Yeah. Now, right. The other thing that I had to explain was that, as you can see, all these functions that we have, they take their variables by value. So like that was drop. This is filter. You know, I taken this auto thing is actually a placeholder for a call by value that I don't care about the type of. Whereas if I had, for example, done this, it would have been a reference to a type that I don't care about. This would have been a reference to a constant instance of a type that I don't care about. This would be an what is called an L value reference of to a constant of a type that I don't care about. And you know, these all sorts of things about the referencing and the R value references and the L value references and all that, with the addition of consts and volatile on top, they have all sorts of implications about the performance, the runtime performance of your code. And usually the least performant is call by value, which is the one that we are doing like for both operands here to filter. This is call by value, as I told you. This one is also call by value, and let me remove that reference in the end. Now, I should tell you that even though in this module we are taking, well, in at least in the practice sessions, we are taking everything in C++ TMP to be call by value, that is completely to the opposite of what is practiced usually in C++. Because, like I have told you all the time, C++ people are very much concerned about their runtimes. The entire reason why we are doing this compile time metaprogramming is because we don't want to spare that in our, well, to waste that runtime in our execution, right? Now, that is fine for us here because, well, all the things that we are doing are pure, but we don't really want to manipulate anything. So we don't need to go for references. And for that reason, we don't need to go for references to consts, which is the normal one when you do like when you want to have a performance function, you do, and you want no manipulation inside that function to the arguments that you pass to the function, right? You do a reference to const, right? We don't need that because, well, everything is happening at compile time, and so the extra overhead of copying because of call by value is negligible. It's a part of the compile time. It's not going to hit us in the runtime, right? Now, having said that, so usually call by value is still, even at runtime, preferred for small types. Like for the built-in types, the overhead of adding an extra reference, which amounts to adding an extra pointer at the compiler level, right, is usually more than just dealing with the raw values. So you would rather, if you're passing around an integer or you know, a char or things of the like, you would usually go for call by value. Now, in our case, our lists are actually very compact. They are just a bunch of, you know, bunch of integers, let's say, right? Now, so in our case, even if we wanted to do that at runtime, it might have still been instructive if we had little lists to do call by value. Now, if we knew, for example, that our lists would never get bigger than 10, probably, right? If we didn't have that piece of information, then we should have gone for call by reference, right? Now, so, okay, thank you very much, Daniel. James, for reminding me about that one as well. I got the second yawn from Jan. No?
That was me just opening my mouth.
Okay.
I wasn't breathing in. That was me doing that. I don't yawn that largely, that broadly.
Okay. Okay. Fine. I believe you. Let's see. Now, let me take a look at the time. Okay. So, for this session, I would like to show you a few other things that you you have seen, but you have not. I have not really explained. So, for example, I don't know why I'm getting this breakpoint here. It's strange. Remove breakpoint. Where's that going away? Hang on. Can I start debugging? No, I'm not sure what's going on. Fine. I'll do that later. You probably have seen that I have these things. So for example, in the case of head, right? This is the implementation of head that we talked about in the class. And this is the something that you have been seeing, but I have never explained to you. All right. Now, the role of this is for me to be able to make calls like this one. So, well, so see this line 33. What I'm doing here is that I'm passing the list as an operand to prepend, but prepend comes to the right-hand side. And if I'm not mistaken, James, please correct me, this is called the applicative order. Is that right?
Sorry, do you mind repeating a little bit? I was having a play.
Right. Oh, I see. So like in Haskell, if you do like this one, well, X $F, right? You are putting, this is the applicative order for doing F of, so let's say that this is equal to F of X, right?
No, it's actually $X.
$X. Oh, I see.
Okay.
What is that? Is it this one? Does it's like
no, it's the and sign.
And sign.
Ampersand, yeah.
Okay, I see. So what I wanted to have was to be able to do the and so James, does this have a name? I thought it was the applicative order. Is that correct?
I don't know.
Okay.
I think I don't know.
Okay, fine. Yeah, we'll find out. Now, what I wanted to do was, because I wanted to have a technology similar to what in F# is called piping, right? So in F#, you can do things like well, let me make that a multi-line comment. You can do things like this, right? I think and I think this one comes from OCaml. And then you can pipe this G and then H and then sorry. And then K and so on and so forth. Right? Now, this is useful for when you have a pipeline of functions that you want to apply on, you want to pass an argument to each and every of them. You want to pipeline that. And of course there is this possibility that you can always use the function composition, but sometimes this is more readable, if not all the time, right? So function composition gives you a new function, but it doesn't really pipeline the invocation of those functions on that particular, or the application of those functions on that particular argument, right? Are we clear, by the way, about the piece of intended F# that I have here? Yeah. Now, so I wanted to have this technology, and like I have always told you, no, not always, like I told you once. Let me go to the gosh. I'm going to do this. that. So if I go to operators, the rules for the operator overloading in C++ are quite strict. So like I said, certain operators, even though they are operators from the compiler, sorry, from the language, you cannot overload them. Certain ones, sorry, anything which comes, which is not already an operator in the language, you cannot overload. And even when you are overloading the existing operators, you cannot change their arities, and so for that reason, you know, it was that James couldn't, for example, do ++ for appending to lists. He had to use the regular plus, because ++ is a unary operator in C++, and it's well, plus is the binary one, right? So James had to use the ordinary plus. Now, having said those, what I was trying to say was that this pipe operator, unfortunately, I wouldn't be able to do this one in C++. Now, what I did instead was that I overloaded this operator, the shift to right, or the right shift, right? Now, here's how I did that. So forget about the second overload for the moment. So what I said was that, okay, I want to have a, and this is a global operator. Now, James, I think you once told me in one of the previous sessions that you had failed to you know, define an operator that returns a constexpr. Now, this is an instance of when you can do that.
Yeah, it was for the square bracket one.
Right. Okay. We'll get there. Right. Now, let's see. So back to this case. So what this is saying is that if I'm given an L, a list, right, as the left operand, and an F as the right operand, right, that is as if I'm applying F on L, which is this. Right? Now, this helps me to do things like, well, all of these lines, including this one. So this L5 is a delta, sorry, it's a lambda function that takes an L, and I haven't really put a requirement on it, but anyway, supposing that that is a list, and then it returns you know, these all these things, they are piped up, you know, one after the other. You know, it's a series of things that are piped, you know, on top of one another, and you know, I don't get to put the L dot or you know, the free functions, they don't stack on top of one another. The flow of the execution is the same as the flow of the writing, right? So in order for that to happen, for each and every of the functions that we have had, let me just get rid of this. Right. Okay. For each and every of the functions that we have had, there is an app version. So this is me thinking that this is applicative order. Maybe we realize that that's another name. I don't know. There is a namespace inside the namespace vlist, which is for the list that we are working with, right? That is called app. And for head, for example, there is an applicative head, which does the job for the applicative order. And please forgive my misuse of the terminology if we later on find that applicative is not the right terminology here. Now, the reason why I brought up this for the session is because the technology that I'm using, even though it's not directly a part of C++ TMP, is a technology that I think in C++ TMP you might at some point get to use it, right? So if I had taught you C++ instead of C++ TMP, this would have been a part of what I would have taught you. What I would have taught you, right? Now, I'm not teaching you C++. I'm teaching you C++ TMP, but I think that this is a very useful trick, so I'm going to teach it to you. Now, before I teach you that, Jan, please tell us a joke.
All right. 3 people are stranded on an island, and they also find a magic lamp, like in the last time I told a joke. And they rub the lamp, and a genie comes out, gives each of them 3 wishes. The first one says he wishes for a royal title, a castle, and a way to the castle.
Okay.
Like teleport to the castle. And so genie says, "Yep, that's granted." And he disappears. Second one wishes for a wine plantation, a vineyard, as they're called, a beautiful wife, and for the wife and himself to be transported to the vineyard to take care of it. The last one looks around and says, "Oh, well, like it was just starting to get fun. I'd like a box of snacks, a box of drinks, and the other 2 guys back."
It's getting a little lonely on the island.
I've been told to remove nationalities for these things, so there are nationalities associated. You may guess at them. You may guess at them if you like.
No, don't stereotype. No. No. Okay. Okay, thank you very much. Thank you. Okay, now, so back to business. What this does is that it, for the case of head, for example, now head is a function, right? This head on line 15 is a function. For that, for that function, the correspondence in the app namespace is a struct that overloads this operator, the call operator. Now, this very strange, as usual with C++, this very strange notation is saying that this struct called head, which on purpose is the same name as here, but it could have been anything else, right? This struct, you can pretend that it's a function by calling instances of it, not calling the struct itself, calling instances of it. Using these operands, which in this case is just 1, And the call operator, the function call operator is in C++ this, and it's a member function. And as you can see, that has this trailing const here, because it's a good promise to give to the compiler, so that if you mistakenly alter the GOTS of the struct inside the function, the member function, the compiler stops you. Right? Well, yeah. Now, so what it does is that upon invocation, and not before that, it relays the job using this bit, actually using this bit, to this function. Now, let's go to the usage. Let's say that we are in, well, let's say that we're speaking about this one, right? What we're doing here is that we are creating an instance of the prepend struct which is here. Right, okay. Oh, not that one. This one. We are creating an instance of this struct, which takes a non-type template parameter, and we are passing that instance of that struct as the right operand to the shift right operator, which will then make a call to this operator, which will then call the the instance of the struct prepend with the L, which means that will call that will use this member function, which will relay the job to the ordinary prepend, which is the one that is defined. Now Daniel looks completely puzzled. What is puzzling you?
No, it just seemed like a very roundabout way of
That's true. That's true.
doing it. Yeah.
We could have indeed made so look, this is the ordinary function call, right? We want to reverse the order of operand and the operation.
Yeah.
Right? And in order to do that, we have to,
of course.
right, we have to somehow keep the operation unapplied until the point where we want the application to take place.
Yeah. Okay. Now it clicks. Okay.
Okay. Now, some pieces of terminology here. Structs which do overload, or structs or classes which do overload the function call operator, are referred to in C++ as function objects or functors. Right now, well, in mathematics, functors are functions that take functions and return functions. So, like, for example, the derivation or the integration, right? They take a function and return a function.
Those are functions.
Or in category theory, what was it, sorry?
Yeah. Functions that take functions are called functionals. Functors are mappings, structure preserving mappings. So between categories.
Well, my mistake. They're called functionals. They're not called functors. Right? Thank you. Now, let's see. What was I about to say?
Name of this.
Yeah. Why did we want? So the question is, why did we need in head to become a struct, for example? In order for us to understand that, I would like to show you this one. So we have two versions. We have one version of prepend here. That is a struct. And I'm gonna on comments now. This one, I'm gonna call that prep, which is not a struct. Right? Now, the logic is the same. The only thing is that this is just an ordinary function. Okay. Now let us call that. So let us suppose that instead of that, you want to do this. Right? Now, as you can see here, so what we're doing here is that this is a struct. This bit of it is a struct, and we are producing an instance of that. And we're passing that instance, which is an object. It's not a function. It's an object, right? We are passing that to the function, to the shift right operator. Now, if I instead of that try to call the function, try to pass the function. Yeah? Let me try to compile that. I will get an error message. Oh, let me get this out of the way. Right. I will get an error message. Well, okay, that's telling me that prep was not. Yeah, prep was not declared here. Fine. Now, let's try to understand the error message. Right. Hopefully this is readable enough. What this is saying is that it cannot right. I think this part of it is more understandable. Take a look at the type of the function. So what it's saying is that you are making a call to shift right operator with a list and with a with a lambda, with the lambda expression. Now, your pack is this. Your lambda has this function, this type. Can you understand that type? Can anyone understand that type? And in order to understanding, I need to show you these two lines. Oops. So these two lines. Try to compare it with that. Can anyone, James, can you maybe make sense of the error message with this?
Non-type argument pack. Oh. I feel
Okay. It might
I
be
feel-
helpful if I get you to here. So try to put yourself in the shoes of the compiler. What pieces of information can the compiler figure out given only the line 32, the highlighted part of the line 32? Jan wants to step in,
Is
please.
that the list that it needs a list that's either of a 0 or of a 0 and then const 0? Because I'm not sure what the star means. That's the thing.
That means that if you dereference, so you passing, sorry, you're speaking about this star, right? Right. That means that the function that you have provided is a pointer to this type. So if you dereference that function, if you dereference the prep of 0, which is highlighted up here on line 32, you will get a function that accepts an instance of the type list of 0 and returns
list of 0, 0.
an instance of less than 0 and 0. And remember, so if I just replace that with 110,
It'd be 110 on
can you
both.
see? Yes.
Yep. All right.
See that? Now, is there anything here that you can make sense of? Where is that? Sorry. Let's try to see what is provided to the compiler at this line. You know, we are instantiating prep with 110, right? Now, what is that doing? That is going to here and saying, okay, X here needs to be 110,
yeah.
right? And well, this pack is empty, right? Which means that I will receive a list of 110, which is what you get here.
And then you return a list.
And then
with
you
that.
return, yes, prepend of X to L.
So 110,
right?
100.
Which is the one that you get here.
So you double it then there, which is not
Right.
what you want.
Which is not what you want.
Yeah, because
and you know why that is happening? That is happening because Templar argument. Sorry. Yes, Templar argument deduction happens greedily. Right? Greedily.
Oh, greedily. Sorry. Yes.
Yes. So so that means that, you know, it will not wait until the instantiation time, until the invocation time, where the entire list is provided to it. The rest of this pack is greedily chosen to be empty when we perform the prep call, whereas it is lazily chosen when we do the prepend. Because with the function object, right, you are disassociating the instantiation time from the invocation time. The programmer is manually instructing the compiler to disassociate those two.
Hmm.
Right? So that is the reason why I chose this engineering for, you know, the applicative order. Now that is exactly what I wanted to teach you. In C++ TMP, there are parts that, that there are occasions when you need to instruct the compiler about the stage at which things happen. This is your control mechanism.
Oh.
Right? Now this is not quite C++ TMP, but it's a technique that you will, in real world C++ TMP, want to use. That's the reason why I brought it up. Now, it's instructive that we try at least one instance of these. I mean, I don't want to take a whole session on these. We can go through them, in fact, but I don't know how much instructive that would be. But I'm going to ask you to do. Oh, you have already seen the code, but you didn't pay attention, I hope. For post pen. So please do the post pen for me. You have, let's say, 10 minutes. And I don't know what pieces of information I should, or pieces of code I should provide to you, because this is quite hectic. Well, before anything else, you should first get this. So just write for yourself that. Oh, my apologies, just a moment. Sorry. Okay. So the first thing you need to do is to copy this. And please tell me when you are done with this. Then I will reveal the prepend applicative for you. Okay. Now, Mikhail, please be prepared, because I'm going to ask you to show me my code, your code first. Okay. Is everyone done with this?
No.
Okay. You don't need the second overload for post pen. Only the first one is in. Daniel, are you done? Okay.
I'm done.
Yep.
Okay. Yeah. Jan, are you done? Okay. Mikhail, are you done? Okay. James?
No.
No.
Sorry.
Okay.
I changed
Okay.
my mind
Well,
about how I was going to do it.
okay.
Oh, right.
Just lines 47 and 48 for the moment.
James wants to be clever, so we should let him.
Uh-huh.
Okay.
Oh,
Are we done, James?
Yep.
Okay. Now, let's go to prepend. So this is the prepend version. Now, but by the way, it's also important that you put so you put these into different well, if you don't do with different namespaces, you might end up getting an infinite loop, right? So that's why these are, I mean, that's not the only reason, but anyway, these are in different namespaces. Actually, it's nested. The app namespace is nested within the vlist namespace, right? And so what it is doing is that when it relays the job to the main one, it qualifies the main one with the namespace it is from, in order to prevent infinite call stacks. Okay, now you have 10 minutes to do postpend. And I will go get ready to go pick up my son. Okay, I think you have had 6 minutes, if I'm not mistaken. Is anyone done?
Yeah.
Oh, you are. Okay, excellent. I'm not still done with changing, so you can still have some time. And James, have you also tested your implementation?
Yep.
Okay, very.
I'm now trying to make a little shortcut.
Ah, cool. Seven minutes past. No, 8 minutes. Nine minutes past. Okay, time's up. Ah, Mikhail, are you not done?
Implementing postpend like you did the prepend as a struct operator thing.
Yes, that was your assignment.
Okay, yeah, then I think I'm done.
Oh, very good. Very good. Then I'm gonna stop sharing. And by the way, the other day you guys told me that there is a button that if I press, I can switch between the right.
Yeah.
Between the shares. Now I have just authorized multiple shares, but where is that other other button that you...
Yeah. So now if you click view options, since Mikhail shared,
My options.
view options.
view option.
There should be some green text at the top of your screen. Oh no, that's because I'm viewing.
Yeah.
Where would it be for you? Maybe in the view? No, not in view.
Oh,
Where would it be?
I mistakenly stopped my.
Where is it?
Okay. Full share. Advanced sharing options. One participant, no. Who can share all the participants? Who can start sharing when someone else is sharing host only? Okay. And that's, I can't change that, so. Remote control, management, apps. No, I don't seem to have it. Maybe it's because I'm just the host.
Mm. So it might be somewhere else for you. But where?
Yeah.
Oh.
Yeah, well, let's stop wasting time on that. I'll get that done somewhere. Right. Okay. Let's see your implementation.
Is it cheating just using the old postman like this?
This is not a cheat. That's the
Okay.
entire point.
Yeah, okay.
That's the entire point.
Uh-uh.
You know,
Well,
we don't want to implement it another time. We just want to reuse the implementation, but we want to perform the possibility of, you know, having the applicative order for the same affair.
okay.
Okay. Now let me see. Let me check your implementation. Well, no, well, let's see. Your implementation is not entirely correct.
Okay.
Because the way, but that's only a semantic problem. So the way that we use postpend comes, you get the list, and then you get what you want to postpend something to. Right?
Oh, okay.
Otherwise, I mean, your wiring, your use of the language is right, but you're not quite implementing what we were after.
Yeah.
Okay. So, but that's fine. That's fine. You have done what you could have done. James, do you have something better? Thank you, Mikhail. I'm going to ask James now to share his one with us. His code with us.
Sure. Give me a second.
Oh, by the way, did everyone understand what was on? Oh, you have gone into macros.
Yeah, I'm starting to see if I can
No.
define a macro to do it for me.
Okay, well, good.
It almost works. It almost works. I just have one little tweak I have to make, and then I can just.
No. That's okay. This is nothing that I would show right now.
But this is it done normally. For
okay.
I call it SNOC.
Sure. I mean, well, for the obvious reason.
Yeah. I think it's pretty benign, really.
Yeah.
It's exactly how you did it. So there's the parameter.
Yeah, well, right. Again, the difficulty here is that, I mean, this is not a difficulty. The semantic mistake here is that when you want to do a postpend, you want to have the list first and then what you want to postpend to it.
I know, but it works because it
should work.
It gives me what I want.
Right. Now let me maybe what I'm saying is not completely obvious. So let me just show you what I have. So thank you very much, James. I'll just share my own stuff with you. Oh. Well, actually, my implementation is exactly like yours. So right. Okay. Aha. Right. No, it's not. It's not. The what is different is this, and this is the reason why I think, James, your macros will not work, because some of the times you would want to perform a function call. So the trick with postpend is that postpend is a member function in order for it to preserve that ordering, that semantic ordering that I just explained. Right? And because it's a member function, it needs to make a template call. You see, it's a dot, it's L dot postpend. And because postpend is templatized, right? It needs this why do I forget that? Well, it's not trailing, it's the other one.
Leading.
Leading, yes. Leading template. Right? Now, so are we all good with this?
Yeah. Can I not say, though, that my method is a stylistic choice?
Your method is a stylistic choice. So you
As in
always want
having the argument first.
Right.
Because that's
I mean,
how I see it. I prefer it that way round.
Right.
Sorry to interrupt here. I have to get going.
Yeah, I mean, we'll actually start. We'll stop soon. We'll stop soon. Now you can go, Daniel. You're dismissed. Thank you for coming.
I'll have to leave as well.
Right. Yeah. Bye bye. Right. James. I'm going to ask you to maybe postpone your question to the next meeting session, because I need to go. Yeah. So I'm going to stop the share and also the recording. Right.